Not only are trees interesting and useful in their own right, they give us a lot of information about other graphs. So one of the ways they do that is through the concept of a spanning tree. So the general idea is that you have a graph and you want to understand the sort of crucial structure of this graph. You want to have some sort of skeleton of that graph. Let's see a picture of how this works. So if the graph looks like this, then say I choose this edge, and this edge. They form a connected graph with no cycles, so a tree. And now I have a tree that is somehow spanning up my original graph. It's acting as a skeleton. The other parts are just additional edges that only contribute in the annoying way of creating cycles. So this tree somehow carries some important structure of the graph. So let's see how this is done in general and formally. So if you start with a connected graph, if the graph is already a tree, then you're done. It has nothing superfluous. But if your graph is not a tree, since it's connected, the way it can fail to be a tree is by having cycles. So if your graph has a cycle, remove one edge from the cycle you see first. The remaining graph is still connected. Pause and think why that is the case. Well, the answer is the same answer we've seen several times, that no edge of a cycle is a bridge, meaning that if you have a cycle, then removing any edge will not ruin the connectedness of the graph. Because say I have these vertices V and W, and for connectedness I need a path. But say I now remove this edge. Well, since I had a cycle, I can go along the remaining edges of the cycle and still have my path. So removing an edge of a cycle never disconnects a connected graph. So if now the graph is a tree, then great. If not, then at least it's one step closer to being a tree. Since you ruined the cycle, we need to destroy more cycles. So if it still has cycles, remove one edge from the cycle. Again, you will have a connected graph. If that graph is a tree, you're done. If not, remove one edge from a cycle, and so on. So at each step, you keep the graph connected. And since you started with a graph with finitely many edges, after a finite number of steps, you will have no cycles. That is the source of happiness, because now we have a tree, a connected graph without any cycles. Such a tree is called a spanning tree of G. So it is this skeleton tree that I was talking about earlier. Let us see how this works in an example. So let us look at our graph G, which is this graph. And remember, G doesn't have to be simple, so maybe I have a double edge here. And let me name the edges. So this is E1, E2, E3, E4, and let's call this E5 and this E6. This graph obviously has cycles. For example, I have the cycle consisting of the double edge E6, E5. So I want to remove one of these edges of my cycle. Let me remove E6. So now I have a graph that looks like this. Still, this graph has cycles. For example, I have this cycle that goes E1, E2, E5. It's still there. So E1 is an edge in a cycle. So let me remove E1 as well. So now I have removed E6 and I remove E1. The graph I get now looks like this. But now I have this cycle still. maybe I can remove E4. Let me remove E4. So I remove E6 and E1 I have removed already, and now I remove E4, and the remaining graph looks like this, which has no cycles, and therefore it is a tree. So this is a spanning tree, T. Why did I choose these edges in particular? Well, there is no reason. There are many ways possibly to create a spanning tree. So another way is if in the beginning, say I remove E5, then I get something like this. Then I decide that E6 is one of the edges in a cycle. I mean, I don't decide that, I just see that, so I remove E6 as well. Now my graph looks like this. And then say I remove E3. So I'm removing E5, E6, and E3 because E3 is still in a cycle. So now I get a graph that looks like this. So these two spanning trees look completely different, but they are both spanning trees of my graph. So as we saw in the previous example, there might be more than one spanning tree in my graph G, but they all have the same number of edges. Why is that? Pause and think. The answer is that regardless of this complicated method that I showed you, either way, what I am getting is a tree, and a tree in G with the same vertices as G. So if my graph G had n vertices, it will have n vertices. But a tree with n vertices has n minus 1 edges by the theorem we saw earlier. So all my spanning trees, because they are trees with a specific number of vertices, will have the same number of edges, namely one edge less than the number of vertices. So if my graph G had n vertices and m edges, what I just explained shows that the size of any spanning tree in terms of edges is n minus 1. Any spanning tree has n minus 1 edges. This number carries the fancy name of the cut-set rank of G. So far we have not mentioned anything about cut-sets, so for now this is just a name that people thought was cute enough to give this number. And also, since people think that writing n minus 1 is not fancy enough, we write xi of G. So now we don't have to say how many vertices G has, we just say xi of G. That's the size, the number of edges in any spanning tree of G, which is one less than the number of vertices of G. And similarly, you define something called the cycle rank of G. And this is the number of edges that we removed from G in order to get our spanning tree. So if G had m edges from the beginning, and if the spanning tree has n minus 1 edges in the end, then what we removed was this number, m minus n plus 1. This number is called gamma of G, or the cycle rank of G. Again, so far we haven't talked about what cycle rank means. For now, this is just a name. And these are two invariants now that you can define for any graph, the cut-set rank and the cycle rank.